So my name is Lars-Åke Mattsson. I work at Lindab as a research and development manager, and I have been here for almost 25 years. It's one month left. And I've been working with airtightness all the time, and also have been the convener of working group 3 in technical committee 156, that is ventilation. And there we are focusing a lot on airtightness. So I hope I can show you something and also answer some questions in the end. So I start with the big perspective, and it is those goals, the climate goals that we have, and that has been set from Kyoto. And the first thing here is the 2020 climate and energy package. Next one is 2030 climate energy framework, and then 2050 low carbon economy. But if we start with the first one, 2020 climate action, that is a really important step for us in the world and for Europe, and it has been backed up with a lot of activities, and especially this energy performance in buildings directive. Also, we here in Tightvent, which I am a part of, and has been since the start, and we collect like research findings and so on, and we use that findings to do good products and to do good systems, and present them to everybody so that everybody knows what is good and what is bad, I hope. Our main focus is this build tight, ventilate right, and that is really important, and I don't think any researchers can say that build tight will not make a difference. And if you build tight, ventilate right comes as a very important thing after that, and that's also highlighted now in the energy performance in buildings directive, that we have to focus a lot on the indoor air quality. We cannot only build tight to save energy. We must live in our buildings as well. Then how to ventilate right, that's a little bit more tricky, but if we go to the next part here, I am always talking about this part with a very airtight building, and then mechanical supply and exhaust ventilation with heat recovery, so that we take in the best air available in the building, we use it, we heat it up, and then we use the energy again to heat up the new air coming in. Then we have a very good and healthy building that will work as we say it will. So,
Lars-Åke, we couldn't hear you.
No,
okay,
I didn't say
now.
Anything. Yeah, it didn't work for a while, but now it works again.
Okay.
So airtightness in ventilation duct, what is that? It starts off with this little diagram here that we have, and it's one of the crucial things for airtightness in ducts. And on this part we have the system pressure. It goes from 10 Pascal to 10,000 Pascal. It's perhaps not really relevant, but the standards, they go up to 2,000 Pascals, and that's what we are using. And over time, the pressure has gone down and down and down to low pressure system, because we save energy in that. So the pressures are going down all the time, but this diagram works all the time. On this other side, we have the leakage factor, that is liters per second per square meter. And that is to be able to compare different systems, which is big or which is small. So therefore we have this square meter. And the square meters, that is the area, the surface area of the duct system. And why do we measure that? And really, I don't know, but I think it's has been from the beginning when the researchers started up with this in the 1960s. They tried to find a measurement that was easy to find and also had a good impact on this. So it worked with these straight lines here that is in this diagram, and it really does. So the liters per second is what we blow in, and then we divide by the surface area of the system, and then we have the pressure on this side. So we have safety class D, C, B, and A, where D is the most airtight system, and there's a factor 3 in between them, so that it is a huge difference between D and A. So that has to be bear in mind, and D is really airtight and really difficult to achieve, especially out in the building sites. Here on the production sites or in the test, it can be done, but to have it all the way out to the building site, that is really difficult. So to measure the surface area, there is different types of standards, or there is one standard, EN 14239 surface area, that takes care of both rectangular and circular duct systems. And it has been adapted so that it should be very easy to measure it with a measuring tape or something like that. You measure the straight ends. You don't take care of the bends itself, but you go with that size to the center of the next center line, and then you measure that. So you don't measure anything about the bends or around the T-pieces. But when we go on a reducer, we take the full length out to the reducer where it has changed to the next dimension and say this has the same diameter as this other part. And that is to be able to do the surface area measurement very easy. And how we do it in reality is that we have some kind of fan. This is a very good one, a very easy one to use for everyone. You don't need to be a scientist to use this, because you put in what you want, what type of leakage class you want to achieve, and then you start blowing. You say go up to 400 pascals. That is very common here in Sweden to test airtightness at. But in other countries they test several pressures or one pressure that they are used to. But in Sweden we have 400 pascal. You tell this machine to go to 400 pascal and it measures the flow, and you have said I want to reach safety class C or D, and then it says if it's okay and not. It blows in the air here in this hose, and in this you see here it measures the pressure. And here you can see that we have to make it airtight, where we have like terminal device and so on. So we have some kind of balloons, or we have to seal it off in any way, so we don't have any leakage in this part. So the history, it started off in Sweden, in the university in Stockholm in 1960s, and I saw now in Valerie's presentation it was 1966 that it was stated. I found this Swedish standard that was from 1975, and it refers to building directive in 1972. Then it comes into the Eurovent standards in 1981. And then, at that time, at 1981, they also talked about the percentage. And I've heard that for many, many years, that people want to have how many percentage of leakage is there. This is very difficult to find as a figure, but in the Eurovent standard there is this percentage, and you use this diagram. but it tends to be used less and less. So in 2003, this EN 12237, that has been the major standard for this, occurs. And this is when I started at SEN and working with Airtightness Standards. And then we have the third-party certification. It's the Swedish type approval that has been there for many, many years in Sweden, and now a lot of European producers are always also using this type approval, but it is a Swedish thing, and now this year or last year, Eurovent has started their certification program called ducts, and it's both for circular ducts, for rectangular ducts, plastic ducts. So this is now a European certification program, and I think that is really, really good for airtightness, that we can say that now we are certified and we really produce what we are saying that we are producing. So requirements from other standards. EN 13779 performance requirements, that is from the old Energy Performance in Buildings Directive. That states that all these things down here, that Class B is general minimum requirement for air duct and also minimum for all exhaust air, and so on. This was a little bit unclear, and now in the new standard that has replaced that one, EN 16798-3 performance requirements, that is from the new Energy Performance in Buildings Directive. Then it's very clear, and it says this value shall be minimum Class B, and Class C is recommended, and that's what I think as well, because Class C is a very good class for energy in the energy perspective. If we look at another standard, EN 15780, Cleanliness Standard, then we see that there is minimum tightness classes from basic level, Class B, intermediate, C, and advanced D. And if you go through this standard, you find in some way that this is a typical example of rooms. So low is with intermittent occupancy, and here medium is like hotels, restaurants, school. The normal buildings, they should have medium and intermediate, Class C. And here high laboratory treatments and hospital and so on. And we see a lot of hospitals in advanced system with Class D. So I think this is reflecting a very good way of using the airtightness classes. In 12599 handing over standard, it also reflects the airtightness here, and that is in the completeness checks. And if we look at the next page here, we can see that the ductwork leakage test has to be carried out only in the case of contractual agreement. And I think that is happening more and more now in all the countries that is talking about saving energy. But it's not a law. I don't think it's a law more than in Portugal. So there is different standards, and there is standards for the environment first. That's the most important that we are talking about now. And here we see EN 12237 for circular, EN 1507 for rectangular, and now it comes PREN 17192 for plastic ducts. That is brand new, and it will will come out in this year or next year. So what is the difference between them? And that is mostly this L/A ratio, because for metal duct it has been tested or shown that the L/A ratio is between 1 and 1.5, and that is when you have a normal amount of products, where because the leakage is normally between the products and the ducts in the joints. And if we have 1 and 1.5, then we have a normal system. If we have a system looking like this with many products, then we are way above here, and then perhaps we can have more leakage. But normal system are tending to go upwards towards 1.5, but I don't see that they are over 1.5 at the moment. In the new standards for plastic ductwork, semi-rigid ductwork, L/A ratio should be between 0.4 up to 0.6 meters. So they are much smaller because they have longer ducts and smaller ducts. And then we have airtightness standards on components. For dampers, we have 1751, technical component 15727, and flexible ducts 13180. These two are very similar because they are doing the area calculation in the same way. They put on, since they don't have an area of their own, it's very difficult to use them, and we have to create an area, and that's done by its own area or by putting on a duct that is 1 meter long. And that is for dampers. For technical component, it is the same thing, 1 meter long duct, but a technical component can both have 1, 2, or 3 or a lot of branches. So we put on ducts on each branch, so it will be 1 meter long. And flexible ducts, we use the real area. Oh, here. So if we have a product looking like this, we can have a 0.5 meter duct on this side, 0.5 meter duct on this side. On this product, we need to have 3 ducts, so there will be 33 centimeters on each side. For airtightness standards for air handling units, we have EN 1886, and that is also a different standard that you have to read to find out how to measure that one, with different leakage classes L3 to L1 instead of A, B, C, and D. And then we have the handing over standard 12599, and the difference between that, it is the same standard, but it has different pressures, because then they speak about the pressures in the real building. So next thing is airtightness through damper blade standard, and that can also be a little bit confused, because they are talking about the same thing, and it has a diagram looking a little bit like the same. It comes from EN 1751, and it has the tightness classes 1, 2, 3, and 4 for air tightness through the blade, not through to the environment as the other ones. But then it has the pressure classes A, B, and C. So we can say that our product is good enough for tightness class 1 up to pressure of 1000 Pascal, or up to 2500 or something like that. So the pressure classification, it's also different between the different systems, and it's 500 to 500 here for positive and negative, up to 2000 to 750, and that is for circular metallic ducts. For rectangular ducts, it's different, and we can choose positive at pressure class. So we can choose which pressure class we can go to. So a really stiff system could go up to 2000 Pascal, or another system can go up to 400. And this is because we need to focus also on the costs of the duct. So if you don't need a system that can withstand more than 400 pascals, you should be able to produce an airtight system up to 400 pascal. So that is a cost issue. And here we have this 12599 standard, and here we say that we should be as near to the operating pressure as possible, but we should keep to these clear figures that are here. And then we have the new standards, the non-metallic ducts, and this has been a big job that we have done in our group, and the biggest problem has been that this is much smaller than what we are used to. It has new shapes on the manifolds and other criteria for pressure. Also this L/A ratio has been an issue for that. So we have said that it should be at least 10 square meters as the others, or the whole system. So that is a new thing that we have introduced. The new shape on the ducts has to be measured the exact area, so it's a little bit more difficult to measure the area. New shapes on manifolds, then we should measure the whole surface of the cube or outline. And then we have the same criteria as for 12599 to measure the pressures that it's supposed to be used at. And then L/A ratio is 0.4 to 0.6. And that's the supplier that has recommended that. For the US standards, we can see that they also work with the same thing. And our safety class C is here, and it's their class 2.1. So they have exactly the same thing that we have, but only adapted to their units. And if we see here source comparisons, International Energy Agency, they have made a very big work now to guide people and countries how to do deep energy retrofitting for buildings. And this is this Annex 61. And there they also talk a lot about airtightness. So please read that and see what they have done for findings. And in Sweden, we have this, it's from 2014, but it is a very, very good study. And there is a lot of tests and findings that is connected to the economy. So you actually can see how much money are you saving on doing this, and you can follow this this link to this standard. It is in Sweden, and I will try to make it English, but at the moment it's Swedish, but there is a lot of figures to be studied from scientists. Also, there is a new class here, class E, introduced in Sweden, but I don't think it will be used very much. My view on this is there is no demand from an energy perspective to go to class E. We have a wet cleaning demand, and we have a problem with grease drips on factory processing, and we have smell from garbage ventilation with overpressure. These two, I would say, don't solve that by using class E. Solve that by airtight or downpipe principle. So the grease or wet things doesn't come out of the system. And this one should be solved by using negative pressure instead. Lindab also have this duct leaking calculator. You can follow this link to go to there, and from here you can put in your specific project and find out what is the difference in annual energy saving for each project. And this is a very good way of showing how much money this is in this. And then I have to thank you from Sweden.